Okay, so we were dealing with the function, say y equals 1 over x minus 2. Where is this discontinuous? Right, it's discontinuous at 2. There isn't a value at x equals 2. I get 1 over 0. That's not going to work. So let's ask about the other piece of our definition. What is the limit as we approach x equals 2? And we can do it from each side. So how would I go about evaluating this limit? So then I get x minus 2 over x minus 2 squared. How does that help me? It's still 0 over 0. And then I'd still want to try and reduce it somehow, and I'd end up right back here. While I see multiplying might actually be a good help, I'm not sure that that's the thing I want to multiply by. I think we might actually want to back up because I don't know how to evaluate this limit off the top of my head. There isn't a nice algebraic method that seems to work to clean this out. So let's do this, quote, the hard way. Let's graph it, see what happens. What's this look like? Now I can kind of do this in a hand wavy method if you'd rather. But I think the graph gives us a little insight as to why this hand wavy idea works. When x is very, very close to 2, but still smaller than 2, so we're on the left side of 2. Let's say 1.9. I put in 1.9 here, I get negative 0.1. I do 1 over negative 0.1, I get a negative 10. As I get closer and closer to 2, I'm still using numbers that are slightly smaller than 2. So when I subtract 2, I'm going to get something negative. And 1 over negative small is going to be big, but negative. So I should expect on this side to continue going down. And that would make this limit negative infinity. If I think about what's happening as I come from the right, I'm using numbers that are ever so slightly bigger than 2. When I subtract something, when I subtract 2 from something that is larger than 2, I get something positive. But it's 1 over positive small thing, and 1 over positive small thing is a big positive thing. So I have one side going to minus infinity and one side going to positive infinity. And remember, we said that the idea of infinity is not a number, it's a concept. So that means that on the right side, we're going up without bound, and on the left side, we're going down without bound. But that means that these are limits whose values grow without bound, whether in the positive direction or the negative direction. The value, the output. What happens as x goes out without bound? I can ask this same question, but I want to not think of the 2 as being the important part. I want to think about this part. Whether I am going to the right without bound or the left without bound, I should still be able to try and ask this same question. What happens to the y value if I think of x as going off to the right? And just keep going, or to the left, and just... We're going to play Buzz Lightyear to infinity and beyond. What the hell happens? I don't have this idea now of getting close to a number, right? I'm not getting closer and closer to 2 in the x value. And if we go back to the definition of our limit, we had that x minus a thing. Well, now the a is infinity. Infinity is not a number. So I can just think of, well, if x gets really, really huge, say bigger than some capital M maximum value, then what's happening to our y value? So give me a really big number. Okay, 1,000 minus 2 is still really freaking huge, isn't it? And 1 over that is 1 over 998. Calculators. Really small, right? Let's get bigger still. What if I go 10,000? 10,000 minus 2 is 9,998. And 1 over that is 0.0001, right? Really small. There's another 0 in it. There's some other decimals after that. If I go out another order of magnitude to 100,000 or 1,000,000 or 1,000,000,000 or 1,000,000,000,000, I'm just gonna go out in that positive x direction. This number is just going to get really huge. And 1 over something huge is teeny weeny. So this should go and get smaller and smaller and smaller and smaller and close in on what value? 0. Now, what's the only difference between this and this? Instead of going to positive infinity, we go to negative infinity. What changes in the way I do this setup now? Yeah, but really small in this case actually means something different here. I think of really small as a number who's tiny, right? And what we want to think of in this idea is that my number is still big. It's just going the other way. So instead of thinking of a very small number, I think of small as close to 0. I'm thinking of a number that's absolutely huge, just off on the left instead of off on the right. Isn't this still true? It's just that my huge value is now a negative huge value instead of a positive huge value. If I was at 10,000, I subtracted 2, I got 9,998. If I'm at negative 10,000, I subtract 2, I get negative 10,002. I get more negative. I get bigger in the negative direction. Yes, that should be smaller if I think of left as small and right as big. But I tend to think of out as big and in as small. I think that helps. So this will also be 1 over something really huge. It'll just be a negative something. What's going to happen in my picture?
Well, that picture is gonna go over to the line as a zero. Zero approaching zero.
But what's actually approaching 0 are the y values, not the x. So I'm going to think of what happens as I go off to the right there as my y value getting smaller and smaller and smaller. And I think as I go to the left, my y value is going to get closer and closer to 0. But I'm starting negative, right? So, correct. So as I go to the left, I'm getting less negative. I'm getting closer to 0. I'm coming up on 0. But over on the right, I'm starting at positive. And I'm getting smaller and smaller and smaller. I'm getting less positive. So I'm still going to get close to 0. I'm going to do it in 2 different directions. Over here, I can think of this graph as bending and stretching out in this direction. And I can think of this graph as bending and coming up and stretching out in this direction. But I'm getting closer and closer to 0 in both directions. I talked about this. We gave this line a name. What did we call this dotted line right here? So what's this line? Aha. A horizontal asymptote for the graph of f of x, for f of x, is a line y equals L, where either the limit as we go off to the right, x goes to positive infinity, of f of x is that number, or the limit as we go to the left to negative infinity of f of x is that number. If I think of my epsilon delta idea, what I'm really saying is that you can get as close as you want to 0 within epsilon of 0 by going out far enough. If you wanted to be within 0.000001, well, then I need to know what x value made 1 over x minus 2 smaller than 0.000001. That's how far out I need to go. So instead of thinking of how close to A do I need to get, I think of how far out, how close to infinity do I need to get. But infinity is not a number, it just means go on forever. So as soon as I get big enough, it works for everything out there. So instead of having this little delta interval, I have everything from here that way. And if I'm going to minus infinity, same idea, everything from here that way. I just have to know where the cutoffs are. And that's my interval, my little piece of the x-axis. Only in this case, it's not so little because it's going off to infinity. I'm not really all that chuffed about the formal definition. It is in the textbook if you want the epsilon delta version of this definition. I'm not all that worried about it. Questions? What kind of a function is this? Say again. Rational. Every rational function has at most one horizontal asymptote. But functions that are not rational, things like exponentials, trigonometric functions, logarithmic functions, they behave differently on one side than the other. My favorite example of such a weird function is e to the x. What's the graph of e to the x look like? You have a graphing device. If you do not have a picture in your head when I say e to the x, you should create a graph. More math dance. Make your arms go the way e to the x goes. What's e to the x look like? What about the other side? It's just flat. I've got a horizontal asymptote, but only on the left. On the right, we keep going up. So e to the x is an example of a function that behaves like this. Where the limit as x goes to minus infinity of e to the x is 0, but the limit as x goes to positive infinity of e to the x also grows without bound. So I only have an asymptote on one side. A horizontal asymptote on one side. Some functions have different horizontal asymptotes on different sides. And my example for this is the inverse tangent function, which should have come up in your pre-calc trig class. What's this graph look like? By the way, this is also in the appendix of our textbook. In that chapter, Appendix D, where we did all the trig functions and the trig identities, the graphs are in there too. But look at what's going on as I draw this picture. There's a horizontal asymptote up here for the right. There's a horizontal asymptote down here for the left. Now, those horizontal asymptotes are related to the vertical asymptotes for tangent. Because when you take an inverse function, you switch x and y. So things that were vertical become horizontal, and things that were horizontal become vertical. So let me think about the tangent graph. Tangent goes like this, right? Down on the left, up on the right. What are the bounds where those asymptotes are for tangent? Where is tangent undefined? My trig functions will tell me that. Tangent is sine over cosine, right? You're not allowed to divide by 0. Where is cosine equal to 0? Which angle gives me cosine equal to 0? Up here. If you're at 0, sine is 0. If you're at pi over 2, cosine is 0. And that makes this the horizontal asymptote at pi over 2. On the right, but on the left, it's negative pi over 2. So I have two different asymptotes on two different sides. We will actually run into a lot of functions that behave in this sort of two-sided behavior when we start looking at growth models. I am in the lab. I am precipitating something out of solution, right? I've done this in a chem lab. It's been a long time since I did any sort of chemistry, but I've got a chemistry thing. I'm adding my precipitating agent slowly. I'm titrating or something like that, or I'm just adding it in a dropper. And what happens? A little bit of my precipitate forms, right? And it forms fairly slowly. Then all of a sudden it accelerates, and I get a lot of it. And then it starts to slow down again because I've run out of that item in solution and I have finished my precipitate. So I get a very fast bit of growth, and then it starts to slow down. And that growth looks like this, except it's all positive. This is called a logistic growth model. Chapter 9, I promise we'll get there next semester. But that sort of growth model is limited by the amount of whatever it is that's in the solution in the first place. If I'm looking at a bacterial colony in a petri dish, well, that's limited by the amount of space in the dish and the amount of nutrients in the growth medium and all the rest of that. So my bacteria will grow and then it will run out. So it will have this upper limit, and the lower limit will be however much I started with. So I'll have, as I go this way, that low end. As I go this way, I'll have that high end. It'll look like this. It'll just be moved up a bit. However, I think these two should stay in your head for now, because these are foundational equations, and we should look at them and be able to say, oh, no, I know what happens with this function as I go to infinity or minus infinity. And the same thing with e to the x. Questions? This is a rational function that I just made up. Back in algebra, I was told there was an easy way with a rational function to figure out if it had an asymptote. Does anybody happen to remember what that was? Damn. All right. In order for me to figure out the asymptote of what's going on here, I need to go back to this idea that 1 over something huge is something really small. I want to think about 1 over x to a power. Any positive power. as x gets bigger. The bottom is going to get big, right? As long as I'm taking a positive power, I'm squaring, I'm cubing, even if I'm taking a square root or a cube root, as x gets bigger and bigger and bigger, x squared gets even bigger, square root still gets bigger, right? All of those things get big. 1 over something big is 1. So that limit is going to be 0. And the same thing is true when I go to minus infinity. Even if it's negative, as long as I'm taking some power, that's going to go to 0, a positive power. Pardon my French. So what? What does this have to do with this? I am going to multiply by 1. I'm taking a limit, right? I'm thinking about the limit as x goes to infinity of x squared minus 2 over 3x squared plus 7. I want to take this limit. I'm going to play the game I played before where I multiplied my limit by something to make it easier. And Fiona, this is what you were suggesting, but now I need to use a 1 that's made up of pieces that look like this. And the p I'm going to choose is the highest power that shows up in here. So the thing I'm going to multiply by to make this work is 1 over x squared over 1 over x squared. That's 1. So I'm not multiplying by something weird. And I'm going to distribute this into these things. The algebra makes sense so far? What happens right here? What happens here? Okay. This 2 over x squared, I could write that as 2 times 1 over x squared, couldn't I? The 7, same thing down here. 7 times 1 over x squared, right? Now, rules for limits. I'm dividing, right? That means I can take the limit of the top and the limit of the bottom separately from each other. And that means I can think of the limit as only affecting this part. Because what's the limit of 1? What happens to 1 as x changes? Nothing. It stays 1. Same thing with the 3, right? So I'm going to take this limit and move it to here. And to here. Wait a minute. What are these two limits? They're the same, but I even know a number. I can tell you what number that limit works out to. Because 1 over x squared looks like this thing, doesn't it? So that limit is 0. And this limit down here is also 0. Wait a minute. if this is 0 and this is 0, I get 1/3. I'm done. It turns out that when I am dealing with a rational function, only the highest powers matter. So let me go back to the very beginning and look at this limit again. If I think to myself, I want to ignore everything except the highest powers, this kind of behaves like x squared over 3x squared, but that fraction reduces to 1/3. If x is absolutely gargantuan, does adding 7 after I square really matter? If it's huge and I square it, it gets even bigger, and then I subtract 2. So what? The difference between 1,000,000 and 999,998, nobody really cares if you subtracted 2 there. Those parts don't count. If I am looking at a rational function, I really only need to look at the highest powers. However, what happens here?
Oh, no. Say an hour, so. Go ahead.
I'm only going to have, right. But let me actually think about how many x squareds are on the top here. The highest power is x squared. How many x squareds are on the top? No. How many x squareds are up here? There are 0 of them. So let me actually write it like that. Right? And now if only the highest powers matter, what answer am I going to get out? 0 divided by 1 is just 0. I could actually think of it another way. I could say, oh, I'm going to do this same game, and I'm going to write x minus 1 over x squared plus 3, and I'm going to do 1 over x squared and 1 over x squared, and that's going to give me 1 over x minus 1 over x squared over 1 plus 3 over x squared. And now what happens to everything on the top when I go to infinity? All the stuff on top gives me a 0, doesn't it? I can actually make a general statement. If the power on the bottom is bigger than the power on the top, I get a horizontal asymptote at 0 every time. When the power on the bottom is bigger, my asymptote horizontally is 0. When the power on the top and the power on the bottom match, I just have to look at the coefficients. A 1 and a 3, like we did up there. If the power on the top is bigger, I don't have a horizontal asymptote. That's it. All I have to do is look at the highest powers. That only works when I'm working with a rational function. I'm just going to write capital H, capital A for horizontal asymptote. If the powers on top and bottom are tied, use the coefficients. If the power on top is larger, no horizontal asymptote. That only works for a rational function, polynomial on top, polynomial on bottom. If you have a root or a trig or an inverse trig or an exponential, we got to pay much more close attention. We can't use this idea. There are other ways to evaluate limits that behave like this. We'll see one of them in chapter 4. We'll see another of them in discrete math if you're taking that course, whether that's this year or next year. There's an entire theory about the ways infinities relate. It's particularly important in computer science. Questions? So here comes my weird twist. Here is a function that is not rational. There's a square root in there. So I can't use the same highest power trick. I hate having a trick fail on me, so I want to try and mess with my trick. I'd still like to use it. But when I think about what's going on here, I've got 2x squared under a square root. What happens when you take the square root of a square? They cancel out. So I can kind of think that that top should really not behave like an x squared. It should behave like an x. The square root, the square kind of canceling each other. And that would mean that the power on top and the power on the bottom are really the same. So maybe my trick can kind of work. But instead of just paying attention, let's do the whole thing with the multiplying by 1 over x to a power, right? But I'm going to think of the highest power not as 2, but as 1, because I've got that square and that square root together, and they kind of cancel each other out. So I'm going to say up here, the highest power is just an x. So I'm going to go ahead and think about the limit as we go to infinity. And I'm going to multiply by 1 over x on top and on bottom. Now on the bottom, this is easy. What am I going to get on the bottom? If I distribute this with both of those pieces. Okay, but let's simplify that as much as we can, right? I get 3x over x. 3x over x is just 3. And then I get minus 5 over x. Yes? It's the top part that's a problem. Because I can't just combine these. But if this had a root, I could do that, couldn't I? Then I'd have a root over a root. That's just one big root. If I'm multiplying roots together, I can combine them. They just become one root. So in this case, I can squish these together. And then I take this x squared and I put it on the bottom of this 2x squared. And that becomes a 2. And I take this 1 and I put it over the x squared. And it's all under the root like that. So that works. But now I can play the same game. What happens to this piece? 5 over x. As x goes off to infinity. What was that, Dean? No, what's going to happen to it numerically? If I take the limit, what's going to happen to that piece? I don't want to move it. Say again? Somebody said it. And that means it's going to go to 0, right? So this piece is going to go to 0. What's going to happen to this piece? The same thing. And that means that this value is the square root of 2 over 3. However, because this is not a rational function, that square root is effing with me, this may not be the same on the left side as it is on the right side. I've only checked what's happening as we go to positive infinity. What if I want to do the other side and figure out what happens as we go to minus infinity? Now you might think to yourself, I'll do the same thing. I'll multiply by 1 over x on top and 1 over x on the bottom. And on the bottom, I will now get 3 minus 5 over x. And on the top, I'll take the square root of 2x squared plus 1. And what will I do here? Well, up here, I replace that with a 1 over the square root of x squared, right? This 1 over x looks like that. Except it doesn't. I just made a boo-boo. It's not a huge mistake, but it is a mistake. What is the square root of 9? Okay. If I take -3 and I square it, what do I get? But then when I take the square root, I get +3, not -3. This symbol actually means the positive square root. That's why we put a plus or minus in front of it, yes? What do I know about this value of x? Well, this value of x is going to minus infinity, right? That makes it a negative number. If this thing is negative, this thing should be negative. And that means in order for these to be equal, I get an extra minus sign right there. And that minus sign is going to stay with me. Everything else in the problem works the exact same way, but I end up with an extra minus sign in the problem. And that means that when I do this limit, I get negative root 2 over 3. And if you were to graph this, you can graph this function on your graphing calculator. You will see a different result on the right and the left, looking like our inverse tangent idea, right? One of them's positive, one of them's negative. It isn't always positive on the right, negative on the left. Sometimes it's the other way around. Question. Adding and subtracting infinities is weird. So frequently, I may end up with something that looks like infinity minus infinity. If I used my limit rules and I said I'm going to take the first part minus the second part, then I would have infinity minus infinity. I don't know what that means. I don't know how to add infinities. I don't know how to subtract infinities. I do understand the idea of multiplying really big number and really big number. I understand the idea of dividing really big number and really big number. I can do those things. Multiplying and dividing works a lot better than adding and subtracting. So this sucks. But if I could convert this from a subtraction problem to a problem that was multiplying or dividing, I could fix it. And I can do that if I multiply by 1. I'm going to use this trick over and over and over and over and over. I just have to figure out what the right 1 is. This is thing minus thing. Pattern for the difference of two squares is thing minus thing, thing plus thing. So let me use that expression. And in order to do this limit, root x squared plus 1 minus x, the thing I'm going to multiply by is the square root of x squared plus 1 plus x over itself. That way, that works. That's a 1. What happens on the top? Well, I multiply. First, that's going to give me x squared plus 1. The square root's going to go away. Then I'll get a minus x with a square root and a plus x with a square root, and they're going to cancel. And then I get a minus x squared. What happens in my numerator? What happens up there? There's no power, but there's still something. What's up there? Just the 1. And now, what's 1 over a gargantuan? Notice this is big number plus big number, right? 1 over something huge gives me small. And we're going to go bigger and bigger and bigger. This is going to get smaller and smaller and smaller. That's going to go to 0. This expression, by the way, where I switch that sign in the middle between the pieces, is called the conjugate expression. I like the idea of switching, adding and subtracting to multiplying or dividing. That's what I did here. It is possible to take infinity minus infinity and get any number you want. I could rig this problem and have a 7 or a 13 or a -2. I can make this do anything in the middle as an answer. There are lots of different ways to get different values when subtracting or adding. So be careful when you do these. I will see you all tomorrow for question and answer day on 2.4, 2.5, and 2.6. See you then.